Welcome back for another deep dive. Today, we're going to be tackling electric fields. But instead of equations in textbooks, we're going hands-on.
Yeah, think virtual physics lab.
Ooh, that sounds exciting.
We're diving into an electric field JavaScript HTML5 applet hosted on a website called Open Educational Resources Open Source Physics at Singapore.
So not a research paper this time, but a tool.
Exactly, an interactive tool. And what's really neat is that this applet lets you actually see electric fields,
Yeah?
in action, which
Yeah.
usually is something we just imagine, right?
Yeah, it's like one of those fundamental forces we know is there, but we can't actually see it with our own eyes.
Exactly. And what's remarkable is this applet is designed to work on almost anything: phone, tablet, laptop.
Oh, that's awesome. So it's really accessible to anyone who wants to learn about it.
Yeah, and they even encourage you to share it. You can embed the simulation on your own website.
So making this knowledge free and easy to spread. I like that.
It's a real hallmark of open educational resources. And this website, it really embodies that spirit. They're all about making physics education more accessible, especially with tools like this, open source tools.
Speaking of the website, how did we even find this gem amongst all their resources?
Well, we followed the breadcrumbs, starting with mathematics and narrowing down to primary school numbers from 1 to 100.
And that's where this electric field applet lives. That seems kind of unexpected.
I know, right? Electric fields tucked away in a primary school section. But it just shows how this site connects different areas of knowledge, like physics builds on math, right? And this structure just makes it clear how those fields relate.
It's like a map for exploring ideas.
Exactly. And
Wow.
it's especially helpful for learners who want to dive into a subject without getting lost,
Yeah, you can see the big picture, but also zoom in on those specifics.
And speaking of connections, there's a whole section on this page called Other Resources, and that's where things get really interesting.
Ooh, tell me more about that.
Well, for starters, they have links to other simulations for electric fields.
So it shows that the online education community is all about sharing knowledge, not keeping it locked up.
Precisely. And the link to GeoGebra really caught my eye.
GeoGebra.
Yeah, it's this dynamic mathematics software. It shows just how interconnected these tools can be. Like, imagine visualizing a math equation and seeing its effects in the applet side by side. That'd be amazing.
Okay, now buckle up, because here's the curveball. They even mention Spotify and Notebook LM.
As tools for audio content creation.
Yeah, and I have to admit, I'm not quite sure what that means for learning about electric fields.
It's definitely unexpected, but it makes you wonder about the future of educational tools, right? Could we engage more of our senses in learning? Not just visual, but auditory, too.
That's wild. Instead of just seeing field lines on a screen, what if you could hear the hum of a strong electric field? It'd add a whole new dimension.
It would certainly make learning more immersive. But for now, let's shift gears and actually dive into this electric field applet itself. Imagine holding a positive charge in your hand, and you're about to place it in this virtual space.
All right, I'm ready to play with some virtual electricity. Let's see what this applet can do.
As you bring that positive charge in, you'll start to see, well, the electric field. It's like having a special lens that reveals this force, something we can't normally see.
So I'm picturing like lines or something to show me where the force is.
Exactly. The applet draws these field lines, graceful curves, really, that represent the invisible force field, and they show you the direction of the force and how strong it is at any point.
Okay, so let's say I put a negative charge on the other side.
Mm.
Would the lines connect between them? The positive and negative?
You got it. The field lines would curve between them, showing that attraction, how those opposite charges pull towards each other. And this is where the fun begins, really. You can add more charges, move them around, change how strong they are, and the field lines just adjust instantly.
It's like a digital sandbox for electricity.
Yeah.
We used to do those experiments with, iron filings and magnets back in school, where the filings would align along those magnetic field lines.
That's a great analogy. This applet is like a supercharged version of that, It gives you so much more control to experiment and see how these fields behave. You're not limited to just one or two charges. You can create a whole complex arrangement and see how the fields interact.
And it's not just about playing around, right? This stuff is actually important. Like, electric fields are behind so many real-world things.
Oh, absolutely. Electric fields are essential for how electric motors work. Medical imaging devices like MRIs. This applet, it lets you experiment with those same forces, but in a safe virtual environment.
Speaking of the environment, we talked about this applet being on a website, right? one that's dedicated to open educational resources. What else can you tell me about the website itself?
Well, one thing that really stood out to me was how organized it is. They use a system of categories and subcategories, like those breadcrumbs we mentioned earlier. It starts broad and then narrows down to specific topics.
Yeah, it makes sense. If you wandered into a giant library with no organization, you'd never find anything.
Exactly. And it's really helpful for learners who appreciate structure. Knowing where a specific topic fits within the bigger picture just makes it easier to understand and remember.
Okay, and we were pretty intrigued by that other resources section. On the Applet's page, there were links to other electric field simulations, if I remember correctly.
Yeah, it reinforces the collaborative nature of this whole online learning space. They're not just providing a tool, they're encouraging you to explore further, see different approaches, perspectives on the same concept.
And there was that link to JavaScript, right? Which is like a math software.
Yeah.
I'm still curious about the connection there.
That's where things get really cool. Jdora lets you create these dynamic models based on, well, mathematical equations. So imagine you're working with an equation that describes an electric field. You plug that into Jdora, see it visually, and then test it out in the applet.
Oh, I see. It's like a two-way street between the abstract math and the visual simulation. You can see how they connect.
It highlights how different subjects, different tools can all work together to deepen your understanding.
Okay, let's get back to the applet itself. There's a way to adjust the strength of the charges, right? What does that let you explore?
Yes. That's key for understanding how the intensity of the field changes. It's like turning up the volume, on the electric force.
So if I make a charge stronger, would the lines around it become like more intense, closer together maybe?
You got it. A stronger charge creates a more powerful field, and the applet shows that visually. By making the field lines denser around the charge, it's a direct visual link between the strength of the charge and the impact it has.
So it's like, to use our library analogy again, the difference between a dim reading lamp and a giant spotlight.
Exactly. And this feature lets you explore some more complex concepts, like the idea of superposition. Have you heard of that?
It rings a bell, but I could use a refresher.
Well, superposition basically means that when multiple fields exist in the same space, their effects add together. It's like, think of overlapping waves in a pool.
Okay, so instead of just one charge making a field, I could put several near each other, and the applet would show me the combined field.
Precisely. You could see how the fields from each charge combine to create this more complex overall pattern. It helps you visualize how, unlike physical objects, electric fields can occupy the same space and influence each other.
And this gets us closer to understanding how things work in the real world, right? Because it's rarely just one isolated charge, it's a bunch of them interacting.
Exactly. It's the groundwork for understanding more complex things, like electric dipoles, or even the behavior of charges within a capacitor, which is a device that stores electrical energy.
So this seemingly simple applet can actually help you visualize some pretty advanced concepts.
That's the beauty of these simulations. They let you connect the abstract idea to a visual representation, making them much easier to grasp, And remember.
Okay, so we've talked about adjusting the charge strength, playing with multiple charges, seeing superposition. What other features are worth exploring?
One that stands out is the ability to visualize electric potential, which is another fundamental concept in electromagnetism.
Electric potential.
Yeah.
That's the one they often represent with contour lines, right? Like a topographical map, but for the electric field.
You're exactly right. And just like on a topographical map where closely spaced lines mean a steep slope, closely spaced potential lines mean a strong electric field.
So I could tell where a charged particle would experience the strongest force just by looking at those lines.
Exactly, like rolling down a steep electric hill.
This makes me think about how much we rely on visual aids to learn, even as adults. Like a graph can make a concept just click in a way that words on a page sometimes can't.
Absolutely. Visualizing abstract concepts is powerful. And that's a key takeaway here. This applet, this whole website, they demonstrate how online resources can make complex topics, well, more accessible and engaging.
Like they're saying, don't just read about it, experience it.
Exactly. And on that note, I think we're ready to move on to the final and perhaps most surprising aspect of this deep dive.
Okay, let's do it. Okay, so we've explored this electric field applet, and we've seen how it visualizes those invisible forces, helps us understand those key concepts. But we did leave off on a little bit of a cliffhanger, right? Something about Spotify and electric fields. Still trying to wrap my head around that one.
Yeah, it's definitely the most unexpected part of this whole deep dive. Remember that other resources section on the applet page? They mentioned Spotify and Notebook LM, specifically as tools for audio content creation.
Right.
It really makes you wonder, could we actually listen to electric fields someday?
I'll admit my initial reaction was, like, what does music streaming have to do with physics? But then I started thinking about, how we learn. We rely so much on visuals.
Yeah.
But what about sound? Could we use audio to understand something like an electric field?
It's a fascinating question. Traditionally, learning about physics has been very visual, right? Diagrams, equations, those experiments you can see. But imagine if we could engage our sense of hearing as well.
Yeah.
It could open up, well, whole new ways of understanding.
I'm trying to imagine, what would that even sound like? Like, would a strong field have this high-pitched whine? Or would, like, opposite charges make a crackling sound as they attract each other?
Hard to say, but it's intriguing, right?
Yeah.
We could create soundscapes to represent different fields, like an auditory fingerprint. Or maybe use changing tones to indicate the field strength.
Oh.
Or the movement of charges.
That would be incredible. It could even help people who have difficulty learning visually, To grasp these concepts, sound could provide another layer of information.
Absolutely. It speaks to a broader trend in education. This whole idea of multi-sensory learning. Instead of limiting ourselves to just one or two senses, what if we engaged all of them in the learning process?
Yeah. This whole deep dive has really made me think differently about how we learn. We started with this one applet, but we've explored so much. Those connections to math, to audio tools, to other simulations. It shows just how interwoven learning can be.
That's what's so exciting about online education. It's not just about finding one piece of information. It's about discovering those pathways, those connections between different ideas, different tools. It's like a choose-your-own-adventure approach to learning.
And this page, with its electric field applet, it really embodies that. It's not just a standalone tool. It's like a gateway to a whole network of resources. It encourages you to keep exploring.
Keep digging deeper.
Yeah.
And for those learners who are driven by curiosity, that desire to understand, that's incredibly empowering. These websites and others like it are making knowledge more accessible than ever before.
So we began this deep dive with a simple question. What can this interactive applet teach us about electric fields? But we've uncovered so much more than that. We've seen how online resources are, they're breaking down those barriers to knowledge, fostering collaboration, and pushing the boundaries of how you learn.
And perhaps most importantly, this deep dive reminds us that learning is a journey, not a destination.
There's always more to discover, more connections to make, more questions to ask. So as we wrap up this exploration of electric fields and the tools that help us understand them, we'll leave you with this. What sparks your curiosity? What will you choose to explore next? Because the possibilities, they really are endless.